Hello. So my name's Jon, CEO of Veridise, and I'm here to talk to you about bugs that we commonly find when people integrate ZK circuits into DeFi applications. Okay. Yeah. Oh, there it goes. Okay, a little bit of a delay. Okay, so first let's talk about ZK circuits and smart contracts and how they're different, because this is really where we find common sources of bugs. So for those of you who aren't familiar with ZK circuits, I'm going to describe them very briefly. So there's a couple of properties that we're going to look at about ZK and smart contracts and how they compare and contrast. So specifically, ZK circuits don't have any notion of storage. They're inherently stateless, and this is because they only operate over inputs that are provided to them. Smart contracts, on the other hand, are persistent. They have storage. That's kind of the point of the blockchain. And so typically when people interact with ZK and smart contracts, the purpose is to perform computation in the ZK component and to store that computation in the persistent storage. On top of that, ZK circuits have very restricted control flow, which means that at the end of the day, all computation performed in the ZK circuit has to be straight-lined. And so as a result, there are restrictions and workarounds that people have to perform when they're developing applications in ZK. Smart contracts, on the other hand, allow arbitrary control flow. As all of you know, really you're only inherently limited by the amount of gas that's being consumed. Finally, if we look at the data types that people are operating over with ZK circuits and smart contracts, circuits are operating over this thing called a finite field, where generally the smallest part of the field is bounded by 0 and some large prime, whereas smart contracts usually operate over large integers like uint256 and so on. And finally, if we look at the privacy guarantees provided by ZK circuits and smart contracts, as you people know, pretty much everything is public in smart contracts unless they integrate some sort of privacy layer, which right now is fairly commonly integrated with ZK. And so this is how people typically design these types of applications. So you've got a particular user, let's just say they're on the client side, they invoke the ZK circuit, they provide inputs, private data, etc., and that ZK circuit is going to provide a proof. That proof is going to say that they performed some computation. That proof is then provided to the smart contracts on some blockchain where it's verified, or hopefully verified, and then usually storage is updated on the blockchain, and that's how we tend to see or the model that we tend to see ZK interacting with smart contracts. And so what I'm going to be talking about today is common vulnerabilities that we see when these types of technologies interact. And in order to show you that it's common across different types of different types of ecosystems, different ways of interacting with ZK and smart contracts, I'm going to look at a couple of different languages. And so specifically, we're going to be looking at Solidity and CirCom, Leo, and O1.js. And if we can create kind of a table based off of how they implement some of these properties that we kind of saw previously. So first of all, we can look at the storage types that people are using when they end up storing stuff on the blockchains. So because Solidity and CirCom is going to end up on Solidity, you're obviously going to be storing things in terms of big ints. On Leo, you have access to both big ints and finite fields, but at the end of the day, pretty much everything is finite fields. And it's very similar for O1.js. If we look at control flow, Solidity obviously has arbitrary control flow in the smart contract, whereas things are typically restricted when you end up integrating ZK with a particular language. Leo has recently loosened their requirements where the smart contract portion of an L2con contract is no longer quite as restricted, but there's still some restrictions that you see in Leo. The other thing that we can look at is how people are designing the smart contract. So obviously in Solidity plus CirCom, the smart contract component is designed separate from the ZK component. And so essentially you've got a very explicit ZK portion and a very explicit smart contract portion that have very limited interaction. And it's the same for Leo, where Leo in the language itself is going to separate the ZK component from the smart contract component. O1.js, on the other hand, kind of inlines everything, where when you write an application, you're writing both the smart contract and the ZK portion together, typically. You can also write a ZK circuit separately, but I'm just going to ignore that until later on. And so finally, we can look at how these ZK circuits end up being proven on the blockchain. And so what I mean by this is once you get a proof, what do you do with it? Do you have to go and explicitly verify it as a developer in code, or is it done somewhere implicitly for you? So as we'll see in Solidity and Circom, you essentially have to import a prover or verifier, and you have to verify it very explicitly. And then for Leo, it's very implicit. Basically, the entire proof verification is part of the language, it's part of the blockchain. Inside of the smart contract, you don't have to explicitly verify a particular proof. And O1.js is kind of a weird mix of both, where if you simply write this inline application, everything is done implicitly, but when you write a custom ZK circuit, then you can explicitly, or then you have to explicitly verify it. So that's kind of a lot of information. And so let's first go and look at what these languages look like. I'll give you a little bit of an overview, and we'll start looking at some common vulnerabilities. So first of all, when we look at code, they're always going to be in this order. On the left, we'll see Solidity and Circom, where Circom is always going to be on the top. Solidity is always going to be on the bottom. If we look at Leo, just to give you a little bit of information about how Leo works, this is an older syntax of Aleo for those of you who know Leo, and I use it because it's just much easier to explain. The transition right there, the thing labeled in blue, is always the ZK part, and the finalize is always the smart contract part. Very explicitly separated, very easy to recognize. Finally, O1.js. Everything is in TypeScript. It's all one function, and we'll see, some of the interactions or interesting interactions that you have there. Okay, so with that very quick introduction, let's go ahead and look at some bugs. So the first type of bug that I'm going to talk about is missing state verification. And the reason why I'm talking about this is because, as I mentioned previously, ZK circuits are inherently stateless. And so what that means is they often require the user themselves to go and provide information about the current state of the blockchain so that they can prove some computation over that state. However, the ZK circuit cannot actually check and make sure that that state is correct because they don't have access to it. Instead, this is something that needs to happen on the blockchain side. So what that means is if someone does not actually validate that the state given to the ZK circuit is correct, a user can lie about a particular state. So we can look and see an example of this, where this is the code that we saw a minute ago, because I just skipped to this slide. And basically, let's consider a case where you've got a private ERC20 token where a transfer function is written in ZK. You want to privately transfer tokens. So what can happen here is when you're transferring tokens, one thing that you need to know is the balance of the user. You need to know how many tokens people have to make sure that they're transferring tokens that they actually own. When you interact with the ZK circuit, however, it doesn't know the balance, doesn't have access to the storage. And so the user has to provide that information. And you can see that in all of these languages, when you look at the ZK circuit, you have the from balance, so the balance that users are starting with, and the to balance, the balance that users should end up with. And that's the thing that the ZK circuit is going to prove. It's going to prove that this transfer was successful. Then that ZK circuit can be checked in on chain, it can be verified, and balances can be updated. However, what we can see here is that if a user trusts the input to the ZK circuit, then you can end up, encountering vulnerabilities. So more specifically, you can see on the Solidity side of things, all it does is it verifies the proof and then it updates state. However, it doesn't actually check to make sure that the inputs to the ZK circuit is correct. We found these types of bugs in many applications, and we can see them in different languages as well. So if we look at Leo, Leo doesn't allow state to be accessed inside of the transition function because, like I said, it's purely ZK. And so it has to be accessed in the finalize function. So again, you have to validate state there. And when it's missing, again, it just means that someone can essentially create tokens for themselves. In O1.js, we see a very similar type of application where I'm actually highlighting the wrong area, but if you look at this first line right here, O1.js has this interesting property where you first have to retrieve state, and then you have to assert, so insert a constraint that says the state that I retrieved is actually consistent with the balance. And that's because in O1.js, it's going to provide more information about the current state of the blockchain to the ZK proof that's generated. And so you kind of have this two-step load process. And if you're missing that second step, then it's a bug. I have been told that O1.js has made this a little bit safer by highlighting when people forget that second step, because it is a pretty significant vulnerability. But users can always ignore it by telling the compiler to ignore that warning. Okay, the next thing that we're going to look at is arithmetic denial of services. And so there are a couple of different types of arithmetic denial of services that we're going to look at here. The first one is going to be a bit more specific to cases where the storage type does not match the type of the type of integer that is operated over in the circuit. So basically, you're not operating over a finite field. And so specifically, we know in the ZK circuit, you're operating over a finite field. But on the solidity side of things, you're operating over big integers. And those big integers can fall outside of the range of a finite field. So you might have a case in like solidity where someone assigns something to uint max, but because uint max can't actually be represented in a finite field, it means that your ZK circuit is effectively broken. And so we can see a case right here where exactly that happens. It's not uncommon for ERC20 tokens to just mint max to whoever created the token. And if that happens, then all of a sudden, you're not going to be able to prove anything about that particular token because you can't actually represent the integer in the ZK circuit. If you're using a finite field, you could use an array of bits, but that's relatively uncommon. So this is the first type of arithmetic denial of service that we see specifically in Solidity and L2con. But there's a second one that we're going to look at that is common to these languages that more closely allow interactions between ZK circuits and smart contracts. And so specifically, we know that ZK circuits have restricted control flow. And so because they have restricted control flow, it's the case that they often can't avoid errors. So for example, a lot of these ecosystems want to provide strong security guarantees, and part of that is they provide a lot of different types of integer types and stuff like that that do have overflow protections. So specifically, the integer types in these languages have overflow protections, and it will cause something to revert if an overflow occurs. However, you can encounter problems with this because you effectively have straight line code, which means that it now becomes impossible to avoid an overflow in certain circumstances. And so we can see a case like that here, where we're specifically looking at Leo and O1.js. And more specifically, what you can see is there's this particular ternary operator, which one would typically use in order to avoid an overflow. So basically, if something would overflow, then default to something like uint max, otherwise perform the operation. The problem is, it's always going to execute the operation that will actually cause the overflow. And that's because even when you have a ternary operator, it's going to exercise both sides of the ternary operator. It's not going to short circuit. And so as a result, when you're operating over integer types, this type of behavior will cause an overflow and will cause the application to revert, which has resulted in, or can result, there are bugs that we found during the course of an audit, can result in basically denial of service attacks where certain users can't perform certain operations, particularly when you reach boundaries of integers. Okay, the next thing that we're going to look at is finite field overflows. So I already talked about how ZK circuits can or do operate over finite fields. And the interesting thing is, while a lot of the languages that we talked about incorporate integers in some way, and they incorporate overflow checks when you have an integer, they don't do that with finite fields, which is a bit interesting because finite fields are allowed to overflow, by which I mean if they exceed the prime, then they go back to 0. And so this causes some interesting behaviors that we found users don't expect. So more specifically, you can see here where, again, we have a transfer application, or a transfer in an ERC20 contract. And if someone was going to perform this transfer, they might expect that when someone specifies an amount greater than the input balance, that some overflow check will occur, and therefore the ZK circuit will not actually be able to compute a proof. However, that doesn't occur. It's just going to overflow the field, and therefore you can end up with a very large number when you don't expect, or a very small number when you don't want it to. So basically, if you have a high balance, and all of a sudden you could have a low balance. If you've got a low balance, you could very suddenly have a high balance. So it effectively would allow someone to mint tokens without wanting to. Now, this is even with proper validation of those input values. And so people have to be careful about this when they're operating over finite fields, because even in languages that provide, or specifically in language that provide integers, this is unexpected behavior because the finite field operations differ from the integer operations. So the next type of vulnerability that we're going to look at is proof replay attacks. So very specifically, what a proof replay attack is going to do is a user is going to, execute or invoke some circuit. It's going to generate a proof, and they're going to check it into the blockchain. And you would assume that whenever you generate a proof, you probably only want it to be verified once on chain. But in this case, it can be verified another time or many other times. And so you pretty much always want to ensure that proofs are unique. And what I mean by that is you can only check them into the smart contract once. And so we can look at a couple of ways where this happens. And note, this only happens when a particular language allows explicit proof verification. Because if you're using something like Alio, it's up to the Alio, it's up to Alio itself to make sure that proofs are actually unique, and it's not up to the user. So this only applies to Circom and Solidity and O1JS because they allow explicit proof verification. And we can see how this happens right here. So more specifically, we're going to go back to our transfer example. And so we can see that people are actually, in this case, providing correct requires. They're making sure that the inputs are consistent with the smart contract state. However, you end up having some particular vulnerabilities where essentially, if you ever enter this state again, someone can replay the proof, and therefore they can perform the transfer over again, even though someone might not want to. For those of you familiar with ZK, this means that they need proper nullifier checks, which aren't included. The last type of common vulnerability is privacy leaks, but I'm running out of time, so I'm going to skip this. Basically, we operate over private data in ZK circuits. Very easy to leak that private data. Need to be very careful, particularly when you have data flow from private data to public data, because it'll become public once it enters the smart contract. And that's it. Thank you.